Okay, welcome everyone. So maybe before we begin, like quick administrative things. So as you might have received the notification, I have changed the deadline for the first assignment from today to Thursday night, 10 o'clock. While a lot of you requested for the extension, after the extension, like I also received feedback that maybe I should not have extended in the last minute. But remember, like I don't need to explain this, but still I would like to give the explanation. So it's not like I could plan the extension a week or 10 days before the assignment, because the plan is not to give an extension. So the reason why extension is last minute is you just to accommodate students who started like 1 or 2 weeks later in the course, and also students who are doing the course remotely from different countries and still figuring out how poly system works and like how to like use modal and so on, right? Like, so I am new to poly and I'm still figuring out how the system works. So it's going to be even more harder for students who are starting their masters or PhD completely remotely. So it is mainly to accommodate these set of students that like the deadline has been extended. But as the email said, the second assignment will be released today, and there's no extension. Like it is not going to be postponed because the first assignment deadline is postponed. So the ideal scenario is like if you have finished your A1, submit it and move to assignment 2. Just because there's an extension of 3 days doesn't mean everyone has to utilize it. It's for people like who needed that extension. So it should be the optimal strategy for you is like to finish the assignment today and move on to the next assignment. Okay, so maybe let's begin. Let me share my screen. Okay, so before we start the lecture, so maybe let's go through a quick recap of what we have seen in the previous lecture, since we finished, we did not finish it completely. So in the previous lecture, we started discussing about generalized linear models, right? So these are basically models which has some nonlinear function, right? Like they're nonlinear with respect to the parameters, but the decision boundary is still linear with respect to x, right? So that is generalized linear models, and we started like with an example for a generalized linear model, like which was Gaussian discriminant analysis, right? Like so first we came up with this formulation for two-class problem where you could express probability of C1 given X as sigma of A, right? And similarly, for more than two classes, we came up with a softmax function, which could be used to represent P of CK given X, right? And then we started with like Gaussian discriminant analysis, where there were two basic assumptions. So the first assumption is the class conditional densities, P of xk given ck, or going P of, I think this is just P of x given ck. P of x given ck is Gaussian, right? And the second assumption is all the classes are going to share the same covariance matrix. So also when I introduce these assumptions, like I told you, we will be like removing these two assumptions as we progress. But we did not do that in the previous lecture, but we are going to do that in today's lecture. Okay, so with these two very strong assumptions, like we started deriving GDA. So the probability of x given ck is given by a multidimensional Gaussian, and this is the PDF of the multidimensional Gaussian, right? And we started with the two-class problem where P of C1 given x is equal to sigma of A, where A is given by this ln the term inside the law, right? Okay, so then we basically substituted Gaussian PDF here, and we came up with a final formulation, right? So one thing to remember here is because maybe I should zoom it. Okay, so one thing to remember is like because I had this strong assumption that the covariance matrices are shared, so the x squared terms actually canceled each other. So there are only linear terms of x which is left, right? Like so here you could see that GDA can be represented as W transpose x plus W0, where W is given by this term, right? The first circle, and W0 is given by the second circle, right? Like, so it's exactly here. And we also, okay, so that's wrong. Okay. Oh, I think this is where we stopped. So this is again, this is the GDA model, and we wanted to know what are the parameters of this model, right? So the parameters of this model are mu1, mu2, the means of two classes, sigma, which is a shared covariance matrix, probability of C1, the prior probability for class 1, and P of C2, which is the prior probability for class 2, right? Okay, so then the next question is how to learn these parameters. I think this is where we stopped. So remember that in the case of simple non-probabilistic model like linear regression, the easy way to learn these parameters is by using least squares, right? So you have some model, let's take the linear model, which is WX plus W transpose X plus W0, right? Like just, so if you just have no probability, no sigmoid, just W transpose X plus W0 as the prediction, right? In this case, you would try to minimize the difference between the prediction and the target by using least squares, right? So that is for a model which is not probabilistic. So then we asked this question last week, like, which is, how can I learn the parameters of a model which has this probabilistic nature, right? So one thing that we figured out is like so there is one small mistake from last week. So the objective function that, where is my, yeah. So the objective function that we want to maximize, right? So it has to be like, since this is like a full generative model, like, so we are trying to maximize the probability of C comma X. Okay, so the joint probability of the data and the target. Okay, so how do we do that? We have a data set which has like n data points, right? So now we also consider T of n is equal to 1 for class 1 and 0 for class 0 or class 2, right? Like this is class 2. Now, the probability of C1 is given by pi, probability of C2 is given by 1 minus pi. So then we are interested in computing the probability for any data point, right? So if the data point comes from class 1, then the probability is given by P of xn comma C1, which is P of C1, P of xn given C1, right? Like P of C1 is pi, P of xn given C1 is the first Gaussian with mean mu1. Similarly, if the data point comes from C2, then this is the second term is the probability for that. It's 1 minus pi because it comes from C2 multiplied by the second Gaussian, right? So using these two terms, we came up with a new term, which is called the likelihood of the data point. So the likelihood of the data point tells me what is the likelihood that this particular data point comes from the distribution, right? So now that is simply the first probability if Tn is equal to 1, right? Or the second probability if Tn is equal to 0, right? So, okay, so Krinol, 1 second, let me just finish. And we stopped here when I said, okay, so now that we have a way to compute the likelihood of a data point, like one objective function that we could use in probabilistic model is to maximize the likelihood of all the examples in my training set. Let's say I have a training set which has 10 examples. Now, for each example, I will compute P of x1 comma y1, P of x2 comma y2, right? So for every example in my data set, I'm going to compute the joint probability of the x and y, okay? Now I will maximize this probability so that the model will learn to give high probability to the data that comes from the original data distribution and low probability to data that doesn't come from the original distribution, right? Like, so then that particular probabilistic model is going to become closer to the true model from which the data is coming from. And hence, by using this model and Bayes' law, I could actually come up with right predictions. Okay, so this is where we stopped. Maybe Krunal, you can ask your question now.
Hi, so my question is about the expression for likelihood of a data point.
Yeah.
So I believe there would be another expression where you would not just multiply an exponent, use Tn as exponents, but you can just use Tn as multiplication and add those terms, and that would still give
Yes,
the same.
we are
Why
going
did you
to see
chose
that.
that one, or how did you derive this particular expression?
Can I just repeat the last part?
Yeah, so basically, like, since my basic question is that if this expression is not unique, then why did you choose this one? Or if there is any particular way you derived it, then like, how did you derive it?
For this term, right? Are you talking about this expression?
Yes.
Well, I did derive it from first principles, right? Like, so there is nothing hidden here. So I'm interested in probability of x comma t, right?
Okay.
I'm just decomposing it into cases. So I want to know what is the probability of x comma t, okay? Now there are two cases. Case one is the target is 0.
Mm-hmm.
Case 2 is target is equal to 1. Okay. If target is equal to 0, then okay, take target is equal to 1. If it is target is equal to 1, it belongs to class 1, right? For class 1, this is the probability for the data point by using chain rule. Is that clear?
No, so my is basically, instead of particular expression, also do like t into of x c plus.
Okay, your voice is breaking.
Sorry, my I want to say is that you can also using in you can also say Tn as multiplicative term. Let's put it on in the chat.
No, yeah, I get what you mean. So we are going to change this to the multiplicative term soon. Okay. So I see what you mean.
Something like this. Like
Yeah,
that would also
you
mean
could.
like if Tn is 1, then it would only have the probability of the first class, and Tn is 0.
Yeah. Well, you could do that too. Yeah. So, but the reason why I do like this will become clear like when we move this to like like when we go to the log space. But probably when we go to the log space, we are going to get exactly what you have.
Okay, thank you.
Okay. Okay. So is this clear till this? Like so it's important that you understand the maximum likelihood objective function because this is a totally new objective function that like so far we have only looked at least squares, which is the idea of minimizing the gap between the predictions. Now we are doing something different here. So since this is a probabilistic model, like we are going to use the fact that the model is producing probability to take the data set and maximize the likelihood of the data set. So in some sense, we are trying to fit this model to the target or the source distribution. So there was a hand raise.
Yes, sorry. So it goes on to the question of kernels. So the choice of the likelihood is not unique.
Yes, that is true. Like there are many ways in which you could come here. Like, but we are going to see why I did this like in 5 minutes probably.
Okay, thank you.
Okay, so let us continue. Okay, so we are going to continue from where we left. So just for the sake of having a complete scribble, so I'm going to write down the GDA model again, once again for your revision. So the GDA model is P of C1 given X is equal to sigma of W transpose X plus W0, right? Where W is given by sigma inverse mu1 minus mu2, and W0 is given by minus 1 by 2 mu1 transpose sigma inverse mu1 plus 1 by 2 mu2 transpose sigma inverse mu2 plus ln P of C1 by P of C2, right? So this is what my GDA model is. And we also have the assumption that T of n is equal to 1 for class 1 and T of n is equal to 0 for class 2. Okay, and we also called this to be pi, and hence this becomes 1 minus pi. Okay. Okay, so and we came up with the likelihood term, which is basically pi times this, right? The whole thing power Tn, and 1 minus pi times this, the whole thing by 1 minus Tn. Okay, now we need to maximize this likelihood for the entire data set, right? So for that, we are going to make an assumption that all the examples in the data set are independent and identically distributed. Okay, so this is one of the most common assumptions that most of the machine learning algorithms are going to have. So we will call this assumption as IID from now. Okay, so what is IID assumption? The IID assumption states that all the examples are independent. So if all the examples are independent, then the joint probability of the data set, right? So let's say I have a data set which is a bunch of x1, t1, x2, t2, and so on, xn, tn. This is my data set, right? So the identical distributed assumptions means that like all these examples are coming from the same distribution, okay? And the independence assumption tells us that the probability of the entire data set, which is what we want to maximize, right, is given by product over I is equal to 1 to n, the probability of xi, ta. Okay, so the joint probability of the data set can be decomposed into product of individual data points. Okay, so now I can actually use this IID assumption along with this likelihood term. So let me just copy the likelihood term. Okay. Okay, so now the probability of the entire data set, which is what we want to maximize, given the pi, mu1, mu2, and sigma, okay, is given by product over n is equal to 1 to capital N, the whole likelihood. Okay, is that clear? So now this term is the likelihood of the data. Okay, so now if I maximize probability of D given pi mu1, mu2, sigma, and find those parameters which maximize this data set probability, right? Like the likelihood function. So that is what I'm looking for here. Okay. Okay. Now, how do I maximize this function? Okay. So now we know the usual way, like, so if I want to maximize this function, like all I have to do is differentiate, set it to 0, right? But this is a product of many terms. So one simplification that we are going to do here is to consider the log of this term instead of this term itself, okay? So we are going to do the maximum likelihood solution, okay? But instead of maximizing the likelihood, we are going to maximize the log of the likelihood. Okay, so how do I do that? So instead of taking this term, I'm going to do ln in both the sides. So ln probability of D given pi mu1, mu2, sigma is equal to, so this product term is going to become a summation. Okay, so it's going to be summation over n is equal to 1 to n. Okay, ln pi, the first Gaussian, power t of n, 1 minus pi, the second Gaussian, power 1 minus tn, right? So now this is ln a ln b. It becomes ln a plus ln b. Sorry, this is ln ab, so it becomes ln a plus ln b. And you can also put the tn to the front. So this becomes summation over n is equal to 1 to n. Okay, I'm just bringing the ln inside. So the first term is t power n ln pi normal distribution, right? Plus 1 minus t power n ln, 1 minus pi, the Gaussian. Is that clear? Okay, so now maybe just to make things clear, I will just put the whole bracket for the log. Okay, so now this is my log probability. I just need to differentiate this, set it to 0, so that I get the parameters, right? So now can someone remind me again, maybe in the chat, so what are the parameters that we should find from this objective function? So what are the parameters that we are interested in finding for GDA? Okay, so there is mu1 and mu2, yes. So there is mu1 we need to find, mu2 we need to find. Yeah, there is sigma, which we need to find. And there's also pi. These are the things we need to find. Okay, so let's do them one by one. So I'm going to take this function and copy to the next page. Okay, so this is my term. Okay, so first let's do maximization with respect to pi. Okay, so if I'm just maximizing with respect to pi, what are the terms that would go away, right? So now this becomes summation over n is equal to 1 to n, okay, t power n. So this term is again ln ab. So ln pi plus ln normal, right? So ln normal is a constant. It has nothing to do with pi. So this term just becomes t power n ln pi. Similarly, the second term becomes 1 minus t of n ln 1 minus pi. Okay. Plus there are many other terms here like which we are going to treat as constant. Okay. Now this is the simplified function. So now you differentiate this with respect to pi and set it to 0. Okay, so this is a very simple differentiation. So n is equal to 1 to n, t power n, ln pi, if you differentiate, you get 1 by pi, plus 1 minus t power n, ln 1 minus pi, you're going to get 1 minus pi. You differentiate 1 minus pi, you're going to get another minus 1. So the whole thing is equal to 0. Okay, so now I just need to do a bit of algebra. So this becomes t power n, so t of n, 1 minus pi plus 1 minus tn. Okay, maybe I need a minus here. Pi divided by pi into 1 minus pi. The whole thing is equal to 0. So since we are differentiating, since we are setting it to 0, the denominator would vanish, right? So we just have the numerator. So this becomes summation over n is equal to 1 to n tn minus tn pi minus pi plus tn pi is equal to 0, right? So now these terms cancel. So we have summation over n is equal to 1 to n times tn, and you have n times pi. So minus n pi is equal to 0. Okay. So pi is given by summation over n is equal to 1 to n tn divided by n. Okay. Okay, so now what does this mean intuitively, right? So intuitively, this means that the prior probability for class 1 is given by the numerator, which is basically the number of class 1 examples, right? So tn is equal to 1 only for class 1. It's going to be 0 for class 2. So the number of class 1 examples divided by total number of examples, right? So another way to write this is, let's say n1 is the total number of examples in class 1. n2 is given by the total number of examples in class 2. Okay, so now maximum likelihood solution for pi is given by n1 divided by the total number of examples, n1 plus n2. Okay, similarly, this is the prior probability for class 1, right? So now you know the prior probability for class 2. It's basically 1 minus pi. So it's going to be n2 divided by n1 plus n2. Okay, so we have a solution for finding pi, and it is a very intuitive solution. This is what we would do even if we had no clue about maximum likelihood, right? Like, so intuitively, like if I ask you what is the prior probability for class 1, then you would look at the data set, and if the data set has 70% class 1, then probably like it's 70%, right? So that is what maximum likelihood solution is also giving us. Okay, so now let's do the maximization with respect to mu1. Okay, so to do maximization with respect to mu1, let's go back to this equation. So you see that mu1 exists only in the first term. So the second term itself is constant. You don't worry about the second term. It just exists in the first term. So even in the first term can be split into ln pi plus ln normal, and it exists only in ln normal, right? So I can do a lot of simplifications, and it becomes summation over n is equal to 1 to n tn ln normal, right? Plus everything else is constant. Okay, so now this becomes, we know the PDF, so this becomes minus 1 by 2 summation over n is equal to 1 to n t of n. So it's ln of the normal, right? So the normal has a bunch of terms, like there's x of something, and whatever is in the denominator is not like not required now. Like so we would just use the numerator, and becomes xn minus mu1 transpose sigma inverse xn minus mu1. Okay, plus everything else is constant. I have skipped a lot of steps here. They are not crucial. So I like, if you want to do it by yourself, like you would first substitute the PDF of normal distribution in the ln normal, and then you simplify things, you will get this. Okay, but probably that is not very important now. Like what is important is like, how are we, like what is the value of mu that we are going to get from this equation? Okay, so now we differentiate this with respect to mu1 and set it to 0. Okay, so let's look at this term. So this is x minus mu the whole square, right? So this becomes T of n, summation over n is equal to 1 to n, T of n, xn minus mu1, okay? And this is equal to 0. Like the sigma inverse will go to the other side, it becomes 0. This is what you get when you differentiate and set it to 0. Okay, so now this is actually a simple equation, like we can easily find mu1. So let's just expand this first maybe. So summation over n is equal to 1 to n, T of n xn minus T of n mu1 is equal to 0, right? Okay, so now this becomes, okay, so maybe I'll cut paste this. Okay, so now, 1 second. Okay, so now summation over n is equal to 1 to n, T of n xn, this is fine, okay, is equal to summation over n is equal to 1 to n, T of n mu1, right? So now if you just look at the left-hand side, the summation is only for n, so this term becomes n1 times mu1, okay? So this is equal to summation over n is equal to 1 to n, T of n. So mu1 is given by summation over n is equal to 1 to n T of n xn divided by n1. Okay, so now this is my mu1. This is also very intuitive, right? So what does this term tell? So this term tells us that basically take an average of all the data points, like x1 of all the data points in class 1, right? So whenever Tn is equal to 1, you sum those examples like x, divided by total number of situations where Tn is equal to 1, right? So now this is basically mean of all the input vectors xn assigned to class C1. Is that clear? So similarly, it would be boring to derive mu2 because it's exactly the same derivation. So you could know that similarly, this is going to be summation over n is equal to 1 to n, 1 minus Tn times xn divided by n2. Okay. Okay. So finally, only thing that is left is, okay, so there's a question, when can we ignore the normalization denominators and when shouldn't we? Okay, so if the denominator has nothing to do with the parameter that you're maximizing, then you could just ignore them because they go to the right-hand side. Well, technically, okay, here's the thing. If you have a numerator by denominator is equal to 0, technically anything in the denominator would go to the right-hand side and become 0. So you could just focus on numerator is equal to 0. I hope that answers the question. Okay. Okay. So now the finally only thing which is left is maximization with respect to sigmoid, right? Sigma, right? So now maximization with respect to sigma is a bit more involved. So I would leave it as an exercise, but I would just directly give you the answer. So sigma is given by n1 by n times s1 plus n2 by n times s2, where s1 is given by the sample variance for class 1. So it's 1 over n1, summation over n belonging to C1, xn minus mu1, xn minus mu1 transpose. Similarly, S2 is the sample variance for class 2. So it's 1 over n2, summation over n belonging to C2, xn minus mu2, xn minus mu2 transpose. Okay, so now we have found the solution for like the maximum likelihood solution for GDA, right? Like, so we have the equation for pi, mu1, mu2, and sigma 1, which is shared, right? So you will be implementing this algorithm in your second assignment. So it's important that you go through the derivation once again in the reading week, and like try to implement them. Okay, so a quick note. So remember that we had this one strong assumption, like there are two strong assumptions, right? Like the first, like one of the strong assumptions was that the covariance matrix is shared across all classes, right? This is a very restrictive assumption. So if you relax this assumption, okay, and let every class has its own covariance matrix. So sigma, so this says that there's only one sigma, right? Instead, if you're going to have separate sigma for every class, like sigma k for class k, right? So now that derivation, if you start from the scratch, is going to have the quadratic term, x squared terms. So that model is no more linear. It's going to have some non-linear decision boundary, okay? So that situation where you don't have the shared covariance matrix is known as quadratic discriminant analysis, or QDA. Okay, so we are not going to derive QDA, but now you get an idea of how to do these derivations, and the textbook actually has the derivation for QDA. Okay, so now let's look at how these algorithms work in practice. Okay, it's here. Okay, so in this case, this is LDA for a 2-class problem and a 3-class problem. Okay, so remember that LDA is a generalized linear model. So even though it's a nonlinear model, the decision boundary is linear, right? So you can see that in the case of 2D, the 2-class example, there's a single line dividing both the classes, decision boundary is linear. Similarly, in the case of 3-class example, so you see that it's drawing lines between the classes, okay? And can someone guess what type of multi-class classifier we have used here on the top of like LDA? Or maybe as a recap, what are the 3 ways in which you could do multi-class classification? I would prefer a hand raise. Anyone want to answer? Okay, no one wants to answer. So what are the 3 ways in which, like what are the 3 ways that we discussed about taking a 2-class classifier, like instead of doing like how to do multi-class classification, right? Like, so can someone answer maybe either in chat or hand raise? Is the question not clear? Okay, so I think the question is, how do you like what are the 3 ways in which we could do multi-class classification? So when I have, okay, so the left-hand figure is easy, right? Like, so you have 2 classes, you draw a line in between. Now we have seen like multiple ways to do multi-class classification. Like, maybe to be precise, like we have seen 3 ways to do multi-class classification. What are they? Okay, I see some answers in the chat. So remember that you could do either 1 versus 1, right? Like where for every like it's class 1 versus class 2, class 1 versus class 3, and so on. You could do like 1 versus all, right? Or you could use a discriminant based approach. So these are the 3 ways in which like you could do multi-class classification. In this case, like you see a discriminant based solution, like dividing the 3 classes. Okay. So now this is how QDA would perform. So in the case of QDA, it's a quadratic model, right? So the decision boundary is not linear. You can see that for 2 class, this is the decision boundary, and for 3 class, like you have something like this. So now one thing to note is the orange class and green class has a line dividing them. Can someone guess why that is the case? So why is the decision boundary between orange and green linear? Yeah, so yeah, that's right. So as many of you guess in the chat, they have the same covariance matrix, right? So you have the flexibility. You could say that, okay, these 2 classes should have same covariance matrix, this class has separate covariance matrix, and so on. And even from the figure that you could see that the contours are exactly same for both. So like in this case, they do have the same covariance matrix. Okay, so that is good. So now let's try to summarize. So we had a very lengthy discussion starting from last lecture on GDA. So let's try to summarize. So we are looking at generative models for classification. So the basic idea is to compute P of X given CK and P of CK, right? And then use Bayes rule to compute P of CK given X, right? And to do that, we have seen 2 models so far. The first model is GDA, and the second model is QDA. In the case of GDA, the class conditional densities are Gaussians with shared covariance matrix, right? But in the case of QDA, the class conditional densities are Gaussians with separate covariance matrices. Okay, okay. Now, here is a quick exercise. So let's say I'm doing a K-class problem and I have M features. Okay, now let's first take GDA model. So how many parameters do I need for the mean in GDA model? I have K classes and M features. So maybe we could answer in chat, how many parameters do we need for the mean of the GDA? So there are K, it's not just K, right? You have K classes and each class has a M dimensional data. So you need KM parameters, okay? And how many parameters do you need for the covariance matrix, the shared covariance matrix? So X is M dimensional and you have a covariance matrix. So it's like half of the matrix is going to be repeated, right? So you have M into M plus 1 divided by 2 parameters, okay? And how many parameters do you need for probability of CK? The prior probabilities. So there are K classes. So all the probabilities should sum to 1. So you only need K minus 1 parameters. Okay, so now this is for GDA. Now let's do the same for QDA. In the case of QDA, I would require the same Km parameters for mean. Okay. The covariance matrix for K classes, I'm going to have K different covariance matrices. So it's going to be K times M into M plus 1 by 2. And this is going to be the same K minus 1. Okay. Okay. So now here is the thing. QDA has way more parameters than GDA, right? So this model has more parameters. However, that doesn't mean that we should use GDA instead of QDA. Why? Because GDA is actually more restrictive. So we prefer a nonlinear model like QDA, but it has a lot of parameters, right? Like, so now how can we scale it up, or like how can we have a nonlinear model but still have lesser parameters, right? So to do that, we are going to introduce another assumption, okay? So which is known as the naive Bayes assumption. Okay, it's a very simple assumption, and it's also one of the most common assumptions that people make. So the idea is this: the features are conditionally independent given the class label. Okay, or in other words, if I have P of X given CK, which is basically P of X1 M given CK, I have M features. So the one reason why matrix is big is because there are M features, order M square parameters, right? So what if I make this strong assumption that this joint can be approximated by product over I is equal to unto M just P of Xi given CK? Okay, so what does this mean? This means that the individual features are independent given the class label. Okay, so now this means that the covariance matrix is going to be diagonal. Okay, so we are going to call this model, which has this naive Bayes assumption, as Gaussian naive Bayes. Okay, so now let's look at the parameters required for Gaussian naive Bayes. Okay, so let's look at the parameters required for Gaussian naive Bayes. So you have the mean, which is given by how many parameters? It's Km, right? Now the variance has become a diagonal matrix. So for every class, you only have M parameter. So if you have K separate variances, even then it is only Km. And P of CK is given by K minus 1 parameters. Okay. Now just to compare this with QDA, QDA needs Km mean, K times M into M plus 1 by 2 variance, and K minus 1 parameters for prior probability for this. Okay, so now the Gaussian naive Bayes, it requires lesser number of parameters, but it still has nonlinear decision boundary. Okay, so now a couple of notes. The first note is if you share the diagonal covariance matrix, okay, you're going to go back to the linear decision boundary. So a Gaussian naive Bayes with linear decision boundary is going to be called as a diagonal GDA. Okay, and so far we have seen 4 variations, right? So what are the 4 variations? We have seen GDA, which is a linear model with linear decision boundary, nonlinear model with linear decision boundary, right? So then we have seen, probably I would do the summary before taking the break. So we are dealing with, in the case of continuous input features, okay, so there are 2 possibilities. Like one is whether the covariance matrices are shared or not shared. Okay. Now, similarly, whether the covariance matrices are arbitrary or diagonal, right? So the first model that we saw, GDA, has shared covariance matrix, but it has arbitrary structure, right? Now, QDA is arbitrary, but not shared covariance matrix. Now, when you make the naive Bayes assumption, QDA becomes Gaussian naive Bayes and GDA becomes diagonal GDA. Okay, so now to classify these models, so they don't share. So these are non-linear. So these are richer models. On the other hand, when you share the covariance matrix, which is a very restrictive assumption, then you have linear decision boundary. Okay, so this summarizes like 4 different algorithms for generative, like for classification. Okay, so now we will take a short break. We will start at, well, let's start at 1:45 still, and look at the discrete version of these algorithms. Okay, I'm going to stop the recording now.